Welcome to This Explainer. Look, if you're an executive running a massive construction project, diving into dense engineering protocols can honestly feel like trying to read a foreign language. But hidden right inside all that math are your absolute biggest liabilities. So, let's translate these blueprints into some actionable risk management, shall we? Let's get right to the bottom line up front. In structural engineering, success is absolutely not about raw output or rushing the schedule to save a buck. It is entirely about absolute precision. Trusting the blueprint and relying on rigorously tested methods over guesswork is exactly how you mitigate liability. Because mastering foundational concepts, ensuring accuracy and conceptual clarity will always trump simply getting things done quickly. Here's our briefing itinerary for today. We're going to cover structural analysis frameworks, concrete quality and standards, reinforcement and design rules, pre-stressed concrete systems, and finally, error prevention and execution. All right, Section 1, Structural Analysis Frameworks, the math behind stability. Right at the starting line, your engineering team faces a critical A versus B choice, force methods or displacement methods. And the diagnostic rule guiding this decision is incredibly straightforward. They have to choose based entirely on the specific unknowns they're solving for. If static indeterminacy is less than kinematic, well, they use force methods to find redundant forces. But if the reverse is true, they pivot to displacement methods to calculate how much the structure will actually move or bend. If they pick the wrong path here based on the structure's indeterminacy, your team is going to waste hundreds of hours on completely compromised calculations. Now, that brings us to the principle of virtual work. Think of it as the ultimate mathematical bridge connecting internal equilibrium to external displacement. By synthesizing statics and kinematics, this principle calculates the true structural displacement. For you, as an executive, the so what here is simple. This is the foundational concept ensuring our mathematical models map perfectly to real-world physical behavior. It is literally the math that ensures your building doesn't sway unacceptably in the wind. Moving right along to Section 2, Concrete Quality and Standards, Material Science on the Critical Path. When we dig into the IS 456 exposure rules, pay special attention to those extreme exposure parameters. Environmental exposure directly dictates the chemical makeup of your concrete. From mild all the way up to extreme exposure, there are exact parameters for minimum cement weight, maximum free water to cement ratios, and the minimum grade of reinforced concrete. And listen, these aren't just gentle suggestions for your contractors. They are absolute baseline compliance metrics. If your site is coastal and a contractor tries to save a little budget by using a mild water to cement ratio, they aren't saving you money. They are building a ticking time bomb of corrosion and liability. People often think concrete just dries, right? But actually, scratch that. It chemically cures. It's a continuous exothermic process, meaning it generates intense heat. Managing this exothermic reaction is a massive risk mitigation step, especially for huge pores like dams or really thick foundation mats. If your team doesn't explicitly mandate low-heat cement for these massive structures, the thermal gradients will literally tear the foundation apart from the inside out before the building is even occupied. So, here is exactly where project management clashes head-on with physics. Notice this timeline escalating from 16 hours for basic vertical formwork all the way up to 21 days for heavy beam props spanning over 6 meters. Project managers almost always want to claw back schedule delays by pulling supports early, but gravity does not negotiate with your Gantt chart. Pulling these even a single day early ahead of this 21-day code for long spans can permanently compromise the entire structure. Speed absolutely cannot come at the cost of the chemical curing process. Okay, Section 3, Reinforcement and Design Rules, Fail-safes, and Fatal Flaws. Now, here's a massive, kind of counterintuitive business risk. You might naturally think, hey, more steel is safer, right? Well, no way. It's actually a critical liability. Why? Because if an under-reinforced beam is overloaded, the steel yields first. It sags, it cracks open, and it gives everyone inside ample time to evacuate. But an over-reinforced beam? It fails suddenly and violently as the concrete just crushes under the pressure, without any warning whatsoever. This brittle failure is strictly prohibited by building codes, and your QA teams must guarantee designs are fundamentally under-reinforced to ensure a ductile, predictable failsafe. Similarly, when your internal teams or third-party auditors are out there inspecting vertical load-bearing elements on your site, they have rigid, non-negotiable geometric rules to verify. We're talking a minimum of 4 longitudinal bars for rectangular columns, 6 for circular, minimum 12mm bar diameters, and strict slenderness ratios for short columns. There is zero gray area here. If these specs are missed, the vertical load path of your building is fundamentally compromised, dramatically increasing the risk of a pancake collapse. Let's pivot to Section 4, Pre-Stressed Concrete Systems, Advanced Load Management. It's crucial to understand the core difference here. Pre-tensioning stretches the wire before the pour, relying entirely on the concrete's chemical bond as it cures around the wire. And this demands a premium, high-grade M40 concrete. Post-tensioning, on the other hand, uses physical anchor plates at the ends, pouring the concrete first and tensioning the wire later. That places the structural burden directly on those anchors, which allows for a slightly lower M30 grade. Knowing exactly which system your team is running dictates your entire supply chain and quality control focus. And because of those mechanics, your risk profile shifts. Post-tension systems have literal physical friction as the wire rubs against the duct while it's being pulled. That's a variable that simply doesn't exist in pre-tensioned builds. If your engineers miscalculate this friction loss, the intended tension holding your building up will slowly fail over time. And finally, Section 5, Error Prevention and Execution, QA/QC for your engineering teams. These 4 mathematical traps are exactly where designs fall apart long before a shovel even hits the dirt. Incorrect free body diagrams, slipping up on negative versus positive sign conventions, deflected shape logic errors, and the ultimate killer, basic unit mismatches between meters and millimeters. Think about it. If your calculated beam shape deflects opposite to the actual load direction, the math is just conceptually flawed. An uncaught unit mismatch on a spreadsheet isn't just a typo, it is a multi-million-dollar field correction waiting to happen. You have got to audit for these aggressively. So how do we fix it? Well, we can actually adopt a rigorous study protocol into a continuous corporate QA framework for your staff. First, an 80-20 lockdown. Focus their QA primarily on the highest yield, highest risk structural components. Second, mandate absolute fluency in core formulas so they aren't deriving basics on the fly. Third, master the software interface to completely eliminate input friction and data entry errors. And fourth, maintain a rigorous internal mistake log to isolate and train against recurring failures within your firm. This framework effectively locks in conceptual clarity across your entire team. I want to leave you with a provocative thought to take back to your next management or board meeting. Are you truly certain your engineering teams are prioritizing foundational accuracy over simple speed? Are they actively auditing for these critical calculation traps to ensure conceptual mastery before those plans ever hit the construction site? Remember, in this industry, precision isn't just about making good buildings. It is about safeguarding lives and protecting your enterprise from catastrophic liability. Thank you so much for joining me for this explainer, and I'll catch you next time.